In this section, we will discuss in phase versus out of phase. We will discuss the meaning of in phase and, of course, out of phase, the angular references. In other words, what does 0 degrees mean? What does 360 degrees mean? What does a 180-degree difference between two waves or 2 points mean? We will also discuss how to tell when 2 waves or 2 points on a wave are in phase. So here we go. First, we'll draw a single wavelength. And remember that when we say a single wavelength, we could also say a cycle, and that would mean the same thing. So I'm going to draw one cycle. I'll start here, and I'll draw a crest and a trough. That's one wavelength or one cycle. Now, I'm going to put lots of points on this cycle. There's a point here. I'll put one here and here. Here we go. All right, there they are. Now, of course, I could put an infinite number of points from here to here, but we'll just start with this many. And we'll label these A, B, C, D, E, F, G, H, I. Now, of course, through the center, we have our equilibrium position. Okay, that should be straight. All right. Now, none of these points are in phase with each other. Every one of these positions is unique. Now, I understand that, for example, B and D have the same amplitude. They're both the same distance from the equilibrium point. But you will note that B, since let's say that the wave is traveling in this direction, there's my velocity, you will note that in the next instant, B will be down here. So B is actually heading downward, while D in the next instant will be up here. When this part of the wave moves on to D, D will be up here. So D will be heading in this direction. So even though they have the same amplitude, they're going to have different velocities. Now, the same goes for C and G. C and G are the same distance from the equilibrium point. They're both at maximum displacement. But in the next instant, C will be heading down, while G in the next instant will be heading back up again. So I think you can see that none of these points are in exactly the same, are in phase. Now, I will cite one little exception here. A and I are in phase. So now let's start the next cycle. All right, so let me just erase I for a minute and say again that none of the points that you see here are in phase with each other, because none of them are exactly the same amplitude or exactly the same velocity. Remember, velocity includes direction. All right, now I'm going to start the next cycle, and I'll start the next cycle with letter I, because letter I is going to be in phase with letter A. So here comes my next cycle. Right there. And he should be the same amplitude. I'm trying to draw it nicely. Little bit more there. Okay. So now we've got point I, J, K, L, M, N, O, P, and point Q. What we'd like to do now is pick out pairs or trios of points that are in phase. And they would be on different cycles. Well, the first pair of points that I see that are in phase, actually it's a trio of points, would be A, because this is the beginning of a wave cycle, and I, which is the beginning of the next wave cycle, and Q, which is the beginning of the next wave cycle, which would be over there. So A and I and Q are all in phase with each other. What are some other pairs of points that are in phase with each other? How about C? C is in phase with K. They're both crests on adjacent wave cycles. Now we could also have another one over here, and that would also be in phase with C and in phase with K. So C and K are in phase with each other. All right, how about F? Who is in phase with F? Now, you have A, you go up to C, and then down to F. So here's I, up to K, and then down to N. N is in phase with F. F and N are in phase with each other. So you can see there are lots of different places where I can find pairs of points that are in phase. Maybe we should just put down the two troughs. G and O are in phase. Right, there are lots of other answers that we could put down. All right? Now, obviously, points that are out of phase would be A and B. Well, they're certainly out of phase with each other. C and G are out of phase with respect to each other. Okay, so lots and lots of different examples of points that are out of phase with each other. C and O are out of phase. One's a crest, one's a trough. They are out of phase with respect to each other. So C and K are in phase. C and O are out of phase. All right, now let's talk about angles. All right? If the angle between 2 points is 0 degrees or 360 degrees, those 2 points are in phase. Or in phase, or a multiple of whole wavelengths, that's lambda, whole wavelengths apart. Right? If the angle between 2 points is 0 or 360 degrees, those points are in phase. Or they are a multiple of whole wavelengths apart. 1 wavelength apart, or 2 wavelengths apart, or 4 wavelengths apart, etc. I'll show you an example of that in a little while. Right now, let's just look at wavelengths that are right next to each other. Here's one wavelength or one cycle. Here's another wavelength or another cycle. That means that C and K are 360 degrees apart. They are 1 wavelength apart. This is 1 wavelength from C to E. 1 wavelength. Remember, crest to crest is like a 3rd grade definition of 1 wavelength. Let's find another pair of points that are in phase on adjacent cycles and 1 wavelength apart. How about D and L? D and L are 360 degrees apart. They are in phase to each other. They are 1 wavelength apart. This is 1 wavelength. This is the same 1 wavelength. From D to L is the same one wavelength. You can measure a wavelength between any 2 points that are in phase on adjacent cycles, cycles that are right next to each other. You can't go from here all the way to some wavelength 10 cycles down and call that one wavelength. It would have to be the very next cycle. But that's a wavelength, just like crest to crest is a wavelength. And these 2 points are in phase with each other, or 360 degrees apart. All right, let's find one more pair of points that are 360 degrees apart, one wavelength apart. How about H and P? Right, H and P. Right, those 2 points are in phase. Look where they are. Here's the trough. H is just after the trough. Here's O, the trough. P is just after the trough. So these 2 points are in phase. H and P are in phase. They are 360 degrees apart. That's what another way to say in phase, or 0 degrees. And they are one wavelength apart. Exactly one wavelength apart. Okay? So, we've talked about 360 degrees, which is in phase. Right, now let's talk about 180 degrees, which is one example of out of phase. 180 degrees is the most out of phase that 2 particles can possibly be. Now, I'm going to have to very carefully erase my in phase lines here. Very carefully. And then I'll just fix the diagram. So I'm kind of okay with this diagram. I'm liking this diagram. Okay, so we got rid of those. All right, now let's fix these. Repair our little diagram here. There we go. All right. Okay, C, D, E, F, G, H, I, J, K, L. I'm good at this alphabet thing, aren't I? M, N, O, P, Q. That would be R, S. Okay, we don't need those just yet. All right, so 180 degrees apart is one example of out of phase. 2 particles that are out of phase. 180 degrees would be completely out of phase. And the 2 points would be separated by a multiple of a half wavelength. By a half wavelength or a multiple of a half wavelength. So 2 particles, or 2 points I should say. Let's say 2 points. 2 points separated by a half wavelength, by wavelength over 2, or a multiple of a half wavelength. Right, out of phase points would be 2 points separated by wavelength over 2, a half a wavelength, or a multiple of a half wavelength, wavelength over 2. Right, so how would that look? Right, let's take a nice, easy example for starters. 2 points that are 180 degrees out of phase. Let's start with point C, the crest. Name one point that is 180 degrees, or a half a wavelength, away from C. Now, K, the other crest, would be 1 wavelength away. So halfway between that, G, would be a half a wavelength away from C. So C and G are 180 degrees out of phase. That's as out of phase as you can get. Now, what's another example? C and O. C and O are a multiple of half wavelengths apart. This would be from C, this would be half, 2 halves, 3 halves, 3 half wavelengths away from C. All right? Now, let me fix this, because this would have to be an odd multiple. Guys, put the word odd in here, or an odd multiple of half wavelengths. Because obviously 2 half wavelengths would be a whole wavelength, and that's no good. So it has to be an odd multiple of half wavelengths. All right, so C and G are 180 degrees apart. C and O are 180 degrees apart. How did I find C and G? I looked at C, I found K, which is 1 wavelength apart, and I went right in between them and found G, which is half a wavelength away from C. All right? Let's try another example. And it does get tricky, so we're going to have to look at it very carefully. All right, I'm going to erase this down here. So I don't think we need this anymore. You've copied this down, right? And we don't need this anymore. So right now we're talking about 180 degrees apart. And that's one example of out of phase. That's the maximum out of phase that 2 points can possibly be. 2 points, I keep saying particles, 2 points are out of phase, 180 degrees out of phase, when they are separated by a half a wavelength or an odd multiple of a half a wavelength. So it could be 1 half wavelength, 3 half wavelengths, 5 half wavelengths. And again, I'll show you that in just a minute when we draw some more cycles. But let's take a look at this here. Let's find a point that is out of phase, exactly 180 degrees out of phase from B. Now, I'm going to cheat, right? Look, there's J. J is in phase with B. So right exactly between B and J is going to be the point that is a half a wavelength away from B. And that's going to be, all right, not here, right here. All right, now these points are symmetric. So I'm just going to count. We've got from B 1, 2, 3, 4. From J 1, 2, 3, 4. All right, so exactly between B and J, all right, a hump, and then down. From here, all right, a hump, all right, and then up. You've got, that is half a wavelength, or 180 degrees, out of phase from B. So again, 180 degrees out of phase would be B and F. All right, what other pair would be 180 degrees out of phase? Well, whoever is in phase with F, all right, N, would also be 180 degrees out of phase from B. So B and N are 180 degrees out of phase. All right? Maybe we should try one more. All right? We want 180 degrees out of phase. How about from A? Who is 180 degrees away from A? Well, I is 360. I is in phase. So halfway between, all right, E would be exactly 180 degrees out of phase from A. So 180 degrees out of phase, A and E. Or or A and M. All right? Now, I just want to very quickly show you a longer wave so we can look at the big picture here. All right? So, I have a lot more cycles. Here's one cycle. Here's another cycle. Another cycle. Another cycle. Another cycle. My marker is dying. All right, so these are all different cycles. And let's just say, right, this point here, let's label all the points that are in phase. We've got this one, this one, this one, this one, and this one. They're all in phase with this point here. Now, 180 degrees out of phase with those guys would be these guys. 180 degrees out of phase, halfway between those. All right? Those guys are 180 degrees out of phase from these guys. Now, why don't we count the number of wavelengths or half wavelengths between some of these points that are either in phase or out of phase. You fix that. All right, here we go. All right, so from here, all right, we can have 1, 2, 3 wavelengths apart, exactly 3 wavelengths apart would be in phase. Now, what about this point? We said that that point was out of phase. So, how many half wavelengths is that? You've got 1 half, 2 halves, 3 halves, 4 halves, 5 half wavelengths. Again, an odd number of half wavelengths away from this point would be 180 degrees out of phase. So again, this is out of phase, this is out of phase, this is out of phase. And each of these is an odd number of half wavelengths away from this guy. 1 half a wavelength, that's 2 halves, that's in phase. 3 halves would be out of phase. 4 halves would be in phase. 5 halves would be out of phase, etc., etc. So when you have a multiple of wavelengths away, you're in phase. When you have an odd multiple of half wavelengths away, you're out of phase. Now, what about, see, we've been talking about points on a single wave that are in phase or out of phase. What about 2 waves that are in phase with each other or out of phase with each other? All right, here's a wave. Let's go crest, trough, crest, trough, crest, trough. Now, I'm going to draw another wave that is in phase with this wave. Now, obviously, if I started in exactly the same spot and went up when he went up and down when he went down, obviously this wave would be in phase. Crest, crest, in phase. Trough, trough, in phase. These waves would interfere constructively. Crest would meet crest and trough would meet trough. So obviously if I start in exactly the same place and match the wave on top, obviously these 2 waves are going to be in phase and we're going to have constructive interference. But let's try starting in a different spot. Instead of starting over here, I'll start exactly 1 wavelength to the right. I'll start here instead. and I will make another wave that is in phase with this wave. This wave will start here, and he will go up when he goes up, and down when he goes down, and up when he goes up, and down when he goes down. So, crest to crest, trough to trough. All right, if I'm off just a little, forgive me, but crest to crest, in phase, constructive interference, trough to trough. So these two waves are 360 degrees apart, if you will, or 0 degrees apart. They are in phase. Crest meets crest, trough meets trough. Now I'd like to draw a wave that is 180 degrees out of phase to this wave up here. Let's do that. So where do we need to start the second wave? Well, we would need to start the second wave if we want it to be 180 degrees out of phase. We would need to start the second wave here. 180 degrees out of phase from this wave. So here's his trough. So we start here, and this time, trough meets crest. All right, so these guys are exact opposites here. Okay? All right, so trough meets crest, crest meets trough. Trough meets crest, crest meets trough. Because I started a half a wavelength over, this wave is 180 degrees out of phase compared to this wave here. These two waves in the same place and the same time will have destructive interference, destructive interference. They are 180 degrees out of phase, and they will have destructive interference with each other. They will interfere with each other destructively. As a matter of fact, these two, from the way I've drawn it, will completely cancel each other out, and the amplitude will be 0. In other words, you won't see the light or you won't hear the sound. Okay? So this has been a fairly extensive discussion of in phase and out of phase with a little bit of constructive and destructive interference thrown in for good measure.